Hey everyone, welcome back to Calculus 1. This will be lecture 2 of the course, and in this section we're going to begin looking at limits. We're going to walk through some examples that were kind of picked to help develop intuition about limits, and then we'll explore the formal definition of a limit. So let's go ahead and get started. We'll call this section 1.2, Introduction to Limits. So again, we want to start with some examples that are kind of designed to help build some intuition. And so suppose we are asked to sketch the graph of the function f given by this guy right here. Right? So f of x is equal to x cubed minus 1 divided by x minus 1. Now you'll notice from your algebra experience that this function has a problem with its domain. Specifically, the function is not defined at x equals 1. And so we have to restrict the domain to exclude x equals 1. The function is defined everywhere else, however, and we can plot those values. And we see that the function looks a bit like this. Looks like a quadratic function. Indeed, if you were to do some simplification, you would find that this is a quadratic function. So we've plotted the function like so. But notice that I've included the hole here at x equals 1. We have this hole which I have drawn. Okay, now what we're interested in doing is figuring out what's the value of this function as we get very, very close to 1. Now you can probably look here and see that it's going to be likely to be 3. But let's think about the process that's involved. Say we didn't have a nice picture. Okay, so what we want to try to do is we want to try to imagine getting really close to x equals 1, but not actually evaluating the function at x equals 1. So I've got a little table here. And so I've got this table where we're going to kind of simulate our way of thinking about this. So the top row are the x values, and you can see I've plotted, or I've landed in here 0.75, 0.9, 0.99, and 0.999. Now I could continue on. We could get closer and closer to 1. We could plot 0.9999. We could plot 0.99999999, etc. Right? So we can get as close to 1 as we like. It's just a matter of do you want to write it out? And from the other direction, we've got 1.25, we've got 1.1, 1.01, and 1.001. Right? So over here, we're approaching 1 from below, and up here, we're approaching 1 from above. Right? And so if you think about our image, this is x equals 1. So we start by looking at it this direction, and then we can also look at it this direction. Okay? And so what we're interested to know is what is the value of the function as I do this? Okay? And so I've got those values on here. So when x is 0.75, f of x is 2.313. And you can just confirm this by plugging it into a calculator on your own. But then we get 2.71, 2.97, 2.997. Indeed, if we were to continue, we'd get 2.9997, 2.999997. And you can see that we're getting closer and closer to a value of 3. Same story as we approach from the other direction. So we start by getting 3.81, then 3.31, 3.03, and 3.003. And again, if we were to plot values that were even closer, we would get even closer to 3. Okay, and so as we approach from below, we are going up the function like this, which means we're getting closer and closer to a value of 3 on the y-axis. As we approach from above, we would be coming down the function like this, which means we would be getting closer and closer to a value of 3 on the y-axis, but from the other direction. Okay? And so what we would say is that the limit of this function at x equals 1 is 3. Okay, so the limit at x equals 1 of this function is 3. Okay, so this is kind of an informal example of how your brain sort of thinks about these things loosely, right? We're simulating getting very, very close to a value of the function where for which we can't actually evaluate the function. We can't actually plug 1 into the function, but we can plug in numbers that are very, very close to it. In fact, we can plug in numbers that are arbitrarily close to it. We could plug in values like 0.999 dot 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 99, and maybe I got a million nines in here. That the function is indeed defined at that value. If you could figure out how to plug it into a calculator, you could plug it in and you'd get something very, 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 very close to 3. Similarly, I could plug in 1.000 dot 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 01, where I've got maybe a million zeros here. Right now, technically that's not infinitely close, but it's arbitrarily close. And the idea is I could just keep going. I could get as close as I like. Okay. And so as I get closer and closer to 1, the value of the function gets closer and closer to 3. Okay. Here is a kind of an informal description of a limit. And it says, if the function f becomes arbitrarily close to a point L as x approaches c from either side, the limit of f is L as x approaches c. Okay, so what is this L and what is this c? So if we go back up to our picture, if we go back up to our familiar picture, this is c and this is L. Okay, now as we approach c, the value of the function approaches L, right, from both directions. Okay, so this is very important to keep the L's and the C's straight as we go into the definition, right? C is the value on the x-axis that we're approaching that maybe isn't even in the domain of the function, and L is the value that the function approaches. So we see the function is approaching that value. Okay. And so if the function f becomes arbitrarily close to a point L as x approaches c, then the limit of f approaches L as x approaches c. And this can all be notated concisely using this notation here. We say that the limit as x approaches c of f of x, of the function, is L. Okay, and this is the notation that's most widely used to denote limits. We may also see something like this where we say maybe that f of x approaches L as x approaches c. We'll probably use that notation a little bit later in the course, but for now we'll try to stay very formal and kind of stick to what we've written out here as sort of the formal notation. Okay, great. Let's take a look at a few examples. Okay, let's take a look at a few examples. Here's an example. Identify the limit as x approaches 2 of f of x. All right, and so here's f of x. F of x is a piece function, right? It's a piecewise function. It has 2 pieces. So there's a piece that's equal to 1 whenever x is not equal to 2, and there's a piece where f of x is equal to 0 when x is equal to 2. So notice that f of x equals 1. So sorry, f of x equals 1 almost everywhere, and f of x equals 0 at 2. Okay, so really the function is a straight line. It's a horizontal line except for one spot where there's a hole. Okay, and so we've plotted the function here. And so here you can see the value of the function is equal to 1 almost everywhere. It's almost everywhere. But where it's not equal to 1 is here at x equals 2, where we have this. And there's a hole on the line, but it's not that the function is undefined there. It's just that there's a little bit of a discontinuity. So as we approach 2 from either side, what happens? Well, as we approach 2 from above, what is the value of the function approach? Well, the value of the function is equal to 1 everywhere except at 2. Right? So the value of the function equals 1, equals 1, equals 1, equals 1. There's no reason to think if you were on this line that you were going to suddenly jump off the line. And so we would say that from above, the value of the function approaches 1. And similarly below, as x approaches 2, the value of the function is, again, just 1. There's no reason to think that we should jump off the line and go to 2. the value of the function is equal to 1 for all these infinite values that we're traversing, and so we would say that the limit is 1. And so the way we would notate this is we would say the limit as x approaches 2 of f of x is equal to 1. Okay. Now notice that this is not equal to the value of f at 2. The value of f at 2 is 0, right? So even though the value of the function is 0, the limit is not 0. The limit is 1. Okay, so this is a very important kind of example because the function is defined at the point that we're interested in. We're approaching 2. It's defined there, but the limit is different than the value of the function. Okay, so very kind of draws out this subtle reality of limits is that they're not just the value of the function. You're not just plugging in the limit point into the function and seeing what it gives you. It is a different idea altogether, right? You're moving on the function and you're trying to think to yourself, what would it look like the next value should be given where I'm at on the function? Not what is the actual next value. Okay, very good. So this example, our first example, was an example of finding limits numerically, right? And so this previous one is also one like that, where we're just saying, okay, what are the values of the function that we're moving through here? And even though we didn't have to go find anything because this is a very simple function, we know what those values are, and so that informs how we identify the limit. This is an example of finding a limit sort of numerically. Right, just basically evaluating the function near the limit point, which is a totally sound way to do these things. We can also find limits analytically, but we're going to wait on those until a future lecture. What we want to do is we want to kind of stick to this numeric approach, but just know that the way we're doing this is more about intuition than about efficiently finding limits. Okay, so let's take a look at another example. Let's find the limit as x approaches 0 of this function, the absolute value of x divided by x. Okay, and so remember the absolute value of a function, like maybe the absolute value of a number is equal to the positive version of that number. You can think of the absolute value as telling you the distance from 0 that the number is. That's another way to think about it, right? But practically speaking, if you plug a negative into an absolute value, you get a positive, okay? And so here again, we have an issue at x equals 0. The function is undefined at x equals 0. It's undefined at x equals 0. Right, so we can see that the function is not defined at the limit point x equals 0. That just happens to be the value that we're interested in. That's no coincidence, folks. We chose this example because we want to take a look at these ones that we can't directly evaluate. So something like this, one approach would be to think about what happens when x is greater than 0 and when x is less than 0. So let's start by considering values of f where x is greater than 0. And so we can just plug in a few. So if I plug in f of 1, I get absolute value of 1 divided by 1, which is 1. If I evaluate f of 2, then of course I get absolute value of 2 divided by 2, which again is 1. And this goes on, right, etc. So f of 3 is 1, f of 4 is 1, f of 5 is 1, and so on. What happens when x is less than 0, however? Because the absolute value is kind of what is kind of the interesting feature of this function. What happens when x is less than 0? So if I plug in and if I evaluate f of negative 1, then that's equal to the absolute value of negative 1 over negative 1. And so this guy here is now 1, and I'm dividing by negative 1, and so I get a negative 1, right? And so f of negative 1 is negative 1, and the same thing happens for f of negative 2. I get a negative 1, and f of negative 3 is negative 1, and so on. So what you end up with is a function that kind of looks like this. For all of the values of x where we're greater than 0, the function has the value of 1. For all of the values of x that are less than 0, the function has the value of negative 1. right? And then the function is undefined at 0, so you can see I've drawn some holes here, okay? And so what is the limit of this function as x approaches 0? Let's think about the limit from above and below. So if I'm up above here and I'm moving towards 0, x is becoming closer and closer to 0, then the function is moving like this, right? It's a constant, it's 1. And so we would say from this direction that the limit is 1, right? If I'm on this line kind of walking forward blindly, I would expect my next step would be 1. But there's a hole, but still, the limit would be 1. As I get infinitely close to a value of x equals 0, the value of the function is still 1. And similarly for the bottom, if I'm moving closer and closer to 0, but from the negative side, then the function looks to me like it's headed towards -1, right? This is -1. Up here we're at 1, down below we're at -1. So if I'm moving closer and closer to 0, it looks to me like the limit is -1. So from this side it looks like 1, from this side it looks like -1. So what do we do? Well, if you recall the informal definition, the function has to approach L. Let me find it here. So the function becomes arbitrarily close to a point L as x approaches C from either side. Okay, so that's where we have an issue with this example. When we approach from one side, the limit looks like 1. When we approach from the other side, the limit looks like -1. And so here what we would say is that the limit from the left and the right do not agree. And in these cases, we say that the limit does not exist. D and E for short. Okay, so here's an example where the limit doesn't exist. There is no limit at this value, right? They disagree. You get two different answers depending on which direction you're coming from, right? And in order for the limit to exist, they both have to be the same. Very good. Another example. Let's find the limit of the function f of x equals 1 over x squared as x approaches 0. So here we've kind of written it a little bit differently, but just notice that this means the same thing. And so what do we know about this function? What is this function? Well, again, we're going to have a problem at x equals 0, undefined at x equals 0. Okay, but it's defined everywhere else. Let's plug in those values and see what it looks like. So here I've got kind of a crude drawing. If we approach, for all values of x less than 0, the function kind of looks like this. It has this sort of, it kind of comes up and then shoots up towards infinity as we get close to x equals 0. And from the other direction, when x is greater than 0, it kind of looks like the reverse, right? Kind of starts out low and then shoots up towards infinity as x gets closer and closer to 0. So that we can see that as x approaches 0 from either side, the value of the function goes to infinity, right? The value of the function goes to infinity. Now we call this sort of behavior asymptotic, and that's a term that we'll use throughout the class. It'll come up later, and we'll discuss this. We'll discuss it in a lot more detail when we get into things a little bit later. But in this case, what we would end up saying is that the limit as x approaches 0 of 1 over x squared does not exist. Now you may look at this and say, well, wait a second. They both approach the same number, don't they? Don't they both approach infinity? Correct, they do. They both grow without bound as we get closer and closer to 0 from both sides. But the problem here is that infinity is not considered a real number. So infinity is not a real number. And for that reason, we say the limit doesn't exist. So the limit does not exist because the function does not approach a real number. It approaches infinity. It takes off without bound, but it doesn't approach a finite number, i.e. a real number. Okay, so very good. And so we've seen two examples now where the limit doesn't exist. Let's kind of itemize those reasons real quick. So common reasons for the non-existence of a limit. The first one was the first example we saw. F of x approaches different values from the right and left as x approaches c. So that was our absolute value example. From the right-hand side, we approach 1. From the left-hand side, we approach -1. They don't agree, so there's no limit. Okay, so that was the first example. The second example where a limit wouldn't exist is where the function increases or decreases without bound. Right? So increases meaning it goes to infinity, decreases means it goes to -infinity. Either way, not real numbers, limit doesn't exist. And the third example is one that we haven't actually seen an example like this, the third reason for the non-existence of a limit is one where we haven't actually seen an example like this. And we're not going to see one in this lecture, but we will see one later. And that's where the function oscillates between two fixed values as x approaches c, right? And so an example would be like if the function kind of has a look like this, it kind of goes back and forth, right? Like a sine function, for example. But it's not that it just goes back and forth. What actually ends up happening is that it goes back and forth faster and faster until, as you get very, very close to the limit point, the function is oscillating infinitely fast. It's going back and forth infinitely fast. And so you can't actually pin down whether it's at the top or the bottom or somewhere in between. And so the function oscillates between two fixed values as x approaches c. Now we'll take a look at an example in a later lecture. We're not going to do it now. But this is the third case. Okay. So those are kind of our introductory examples. What I want to do now with the rest of the lecture is we wanted to formally define limits and then go through a couple of examples using the formal definition of the limit. And I'll preface just by saying that the formal definition of the limit involves what are called epsilon-delta proofs, right? If you're going to show that a certain function has a certain limit, you would use an epsilon-delta proof, which is basically the definition of a limit. And these can be a little bit tricky for people. Don't get discouraged as we go through this if this isn't super helpful. I include it, and most calculus instructors do include it, but it's not generally something that's emphasized in Calc 1. It's really there to kind of add some intuition and to kind of show you that there's a level of rigor behind this idea that is pretty comprehensive. So here's the formal definition of a limit. We say, let f of x be a function defined on an open interval containing c, and let L be a real number. Okay, so I've got my c and I've got my L. We've seen these before. Okay. Then we say that the limit as x approaches c of f of x is equal to L. And what does that mean? Well, it means that for each epsilon greater than 0, there exists a delta greater than 0, such that if x minus c is less than delta, meaning the absolute value of x minus c, meaning the distance between x and c, if the distance between x and c is less than delta, then the distance between the function and L is less than epsilon. Okay, so as I said, it's a little bit of it's a definition that is really the bane of all Calc 1 students, to be honest, right? So this is a definition that it can be a little bit hairy to understand if the first time you encounter it. So let's try to draw a picture here and take a look at this in a little more detail. So the idea behind this definition is that given an arbitrarily small distance, that's the epsilon. Think of epsilon as a distance away from x, or away from c. Sorry. Think of epsilon as a distance away from c, and it can be arbitrarily small, right? So that's why it says for each epsilon, no matter how small. Okay. So given an arbitrarily small epsilon, an arbitrarily small distance, there's going to be another distance that I can find called delta, such that if x is within delta of c, then f of x is within epsilon of L. Right? If you can set up this relationship where given an epsilon, I can produce a delta, then no matter how small the epsilon is that you give me, I can always find a delta that guarantees that you're within epsilon of the limit, right? And so here's a nice picture just to kind of illustrate this. So you've got a function like this, right? And maybe the limit point is up here. That's the C evaluates to some hole up here, for example. It doesn't have to be a hole, but it's for illustration purposes convenient. And so here's the C. This is the value that we're going to approach from above and below, right? That we've seen already in the numerous examples, right? And if I say that the limit of this function as I approach C is L, then what that means is that no matter how close you want me to be to L, no matter how close, and which is driven by this epsilon, no matter how close you want me to be to L, I can go find a delta that guarantees that whenever you're in here, whenever you're inside this delta neighborhood here, you are necessarily inside of this epsilon neighborhood of L. Okay, and so our task with an epsilon delta proof is to assume an arbitrary epsilon is given and to then identify a delta such that the condition holds, right? So the condition of the definition says that f of x minus L is less than epsilon whenever x minus C is less than delta. You give me the epsilon, I'll go find the delta. That's the idea behind an epsilon delta, epsilon delta definition of a limit. Okay, and so let's do an example. We'll do two examples of this. The first one is going to be a little bit of a cheater example because I'm going to give you a specific epsilon. The second example will be the more general, like for any epsilon. Okay, and so here's the example we want to start with. Given the limit, this limit as x approaches 3 of 2x minus 5 equals 1. All right, so I'm stating this to be true. Right, we're no longer finding the limit. We know what the limit is, but we want to show that it's a limit. Right, so the limit as x approaches 3 of 2x minus 5 is equal to 1. What we want to do is we want to find a delta greater than 0 such that the distance between the function and the limit is less than this epsilon right here whenever the distance between x and the limit value is less than delta. All right, so I've specified that I want the value of the function to be less than 0.01 away from the limit. Now you go tell me how close I need to be to 3 for that to be true. Okay. So the first step of any of these is to just let epsilon greater than 0 be given. Now in this case, actually, we know what the epsilon is, right? So I could say let epsilon equal 0.01, okay? And so we'll start from that. We'll let epsilon equal 0.01. And then, so that's the first step. Just assume that you're given that information. Then step 2 is to go into the function and try to figure out what relationship the function has to the limit. Okay. And what that usually boils down to is taking a look at this right here. So the absolute value of f of x minus L, right? And so what are these things? F of x, that's just given up here. That's the function in question. And L, that's just the limit. So we say the limit of this function is 1. Okay, so just plug those in. F of x minus L. Right, and so 2x minus 5 minus 1, of course, that's just 2x minus 6. And we notice that in this case, we can factor a 2 out of each of these. Right, and so we do that and we get 2 times the absolute value of x minus 3. Okay, now off to the side here, this is kind of a side calculation that you do. Right, and depending on the function, depending on the limit, this part of the problem is going to vary dramatically in terms of difficulty level. Right, so sometimes it's simple like this, other times it's very complicated. But one of the reasons that we do this is we want to take this guy here and re-express it in something that's more useful given our plans to use a delta. Right, and so something to notice is all of these things are equal, right? And so if this guy here is less than 0.01, if and only if this guy is less than 0.01. So that's what I've written out here, right? And this is just the fact that this guy and this guy are the same means that if one of them is less than 0.01, the other must be as well. Okay. All right, and so based on this work here, we can choose a delta. And so I'm just going to tell you what the delta is, and then we'll see why it works. So here we can choose delta equal to 1/2 of your epsilon. So you gave me 0.01 as the epsilon, and I'm saying delta needs to be half of that. Okay, and so we'll set delta equal to 0.005. Now, maybe you already see why that's the case. If so, I congratulate you. If you don't worry. We're going to talk about it right now. Why do we choose this delta? This delta works because here's what we assume, right? Let's assume that we're within delta of 3. So x minus 3, the distance between these, is less than 0.005. Then what happens? Well, f of x minus L is this, 2x minus 5 minus 1. We saw in our side calculation that that's equal to 2 times absolute value of x minus 3. And so this 2 times the absolute value of x minus 3 is less than 2 times 0.005. Now, do we see where that came from? Well, we assume this is true, right? We assume that this part is true. And if that part is true, then that means this x minus 3 specifically is less than this, right? And so this whole expression is less than 2 times this, okay? And what is 2 times 0.005? It's 0.01, which is our epsilon, okay? Right, and so the way that we came up with this 0.05 is we did this work up here, and we saw that this function here is equal to 2 times x minus 3. Well, x minus 3, that's the distance between x and the point of interest here, right? So if I can make this small, then I'll multiply by 2 to get epsilon, right? And so that's what we have. And so what does this tell us? What it tells us is that to have f of x equal 2x minus 5 within 0.01 of 1, the limit, we need to make sure that x is within 0.005 of 3, okay? And so if you want the function to be this close to the limit, then x needs to be this close to the limit point 3, right? If you want the function to be this close to 1, then x needs to be this close to 3, okay? And this is a great way to start a limit examples, like the epsilon-delta examples, because it really is more concrete. We're talking about a concrete distance here, right? But the way to transition now is to think like, okay, well, wait a second. This was a specific example, but I could just as easily say that I want f of x to be much, much closer. Like instead of 0.01, what if I want f of x to be 0.000000001? So what would I do then? What's my delta then? Well, in the same way, delta is just equal to 0.000000001 over 2, right? So you could just divide it by 2 again. And in fact, it makes no difference how small you choose your epsilon to be. Delta is always going to be 1/2 of that, right? If you make delta 1/2 of that, then you will always, the needed necessary criteria will always be met. Excellent. Okay, very good. All right, so let's take a look at an example, very similar example, but one that where the epsilon is not specific. And so we're going to kind of test what I just said, that no matter how small you make that epsilon, it's still just epsilon over 2. Now this example won't be epsilon over 2 because it'll be a different function, but let's take a look at it. Let's see how it works. Show that the limit as x approaches 2 of 3x minus 2 is equal to 4, right? So again, we know the limit, here's the function, and x is approaching 2. Okay, so step 1 is to assume that epsilon greater than 0 is given. Now I'm not going to specify an epsilon, but just assume that I've given you one, and it's a small one. It can be as small as I like. It can be big if I want, but why would I want that? It's small. Small is really what counts here. So I've given you an epsilon. Now you're going to come along, you're going to do a little side calculation. So you're going to say absolute value of f of x minus L is equal to, well, what's f of x? Well, it's 3x minus 2. What's L? L is 4. Plug it in. 3x minus 2 minus 4 is 3x minus 6. And again, I can factor out a 3 from each of these. And so I get 3 times x minus 2. Okay, and so what should I choose as my delta? Well, I'm going to let my delta equal epsilon over 3. Now, specifically because I'm going to make this is my delta, I'm going to make this thing less than delta. And so my limit here will be equal to 3 times delta. And so I just need to make my delta less than that, right? And so if I choose delta equal to epsilon over 3, we get there. So notice that if 0 is less than x minus 2, which is less than delta, namely if x is within delta of 2, then f of x minus L is equal to 3x minus 2 minus 4, which is, we just saw 3x, 3 times the absolute value of x minus 2. Then this here has to be less than 3 times delta, and delta I've chosen as epsilon over 3. Right? And so again, remember this part here we assume to be less than delta. And so that means this here is less than this. Okay. And so, and of course, 3 times epsilon over 3, the 3's cancel and I get epsilon. Okay. So the appropriate delta in this case is epsilon over 3. Now, it's important to notice that both of the examples that we did in the previous 2 examples, they both have a similar flavor, right? Namely, this side calculation here. That's not going to be true in general. In general, these can vary, right? And if this was a quadratic function, you'd get something quite different. If it was a sine or cosine function or something, it'd be very different, right? But this here, these look the same because these are both linear functions. This one was a linear function, and the one up above here was also 2x minus 5. Okay. All right, very good. Let's move on. Proofs like these are very much the subject of a class called real analysis. And real analysis is, you can kind of think of as like calculus 4. So you do calculus 1, 2, and 3, which are kind of like applied calculus classes. And then after that, you go back and study the same stuff from a much deeper and more rigorous standpoint. So in Calc 1, 2, and 3, we're kind of trying to learn how the math works, and we're trying to learn how to use the math. In real analysis, i.e. Calc 4, it's not really called that, but in Calc 4 real analysis, we want to study the underpinnings and see theoretically how does this work and why does this work. And so that is a subject called real analysis. I highly recommend you taking it if you like math. It is a brilliant class, beautiful stuff, and you will walk away from it much clearer head about most things that happen in calculus. But that's not going to be the focus in this class, so that will be probably the end of the limit, epsilon delta limit proofs. Just threw that out there to give you an experience with it, to show you the rigor that's underneath of all of this. And so our focus will be much more on the evaluation of and developing the intuition for limits, right? We're going to be more interested in being able to evaluate them and think about how they work, and then use them to build derivatives and integrals later. So that'll be it for epsilon delta proof. So don't freak out if that was a complete nightmare for you. In the next lecture, we're going to get into more limit examples, and we're going to try to develop an even better intuition about these things, as well as talk about some properties of limits and different things. So until then, take care. Good to see you again. Let me know if there's anything I can do to make the lectures better. I'm trying to optimize for clarity here. So let me know if you have any suggestions, and we'll talk to you all next time. Take care.